Boom. All right, Julie, welcome to chapter 5. Yeah, chapter 5 is ABS, acid, bases, and salts. And this is an amazing chapter on its own. We're going to look at it in a global view. First, we're going to discuss acid, bases. That's the introduction of acid and bases, from history. And then we talk about acid bases according to true reputable scholars in chemistry. After that, we're going to discuss strength of an acid, okay? And then after discussing the strength of an acid, we look at salts, and then we discuss salts, and that is the end. So I don't know the dimension we're going to take this video. This audio may take about 2 or 3 branches, but anyhow it goes, just know that it's divided into acid, bases, and salts. Acid base is the first tranche, while salt is the other tranche, right? All right, good. So let's get started. Now, in 1680, Robert Boyce defined an acid as a substance that changes the color of another substance and loses its chemical property when it comes in contact with a base. So according to him, that when an acid comes in contact with a substance, it loses its color, right? For example, when an acid comes with a blue litmus paper, it changes to red, stuffs like that. Then when it comes in contact with an indicator, it changes the color of that indicator. That is Robert Boyce's definition of an acid. Years later, Antoine Lavoisier came into play and said, an acid actually is made up of oxygen, and oxygen happens to be the most important element in an acid. That what determines the acidity, in quote, of an acid is the presence of oxygen. And he said tetraoxosulfate 6 is an acid, phosphorate is an acid, triazole 95 is an acid, stuffs like that. Then Davies in 1811, Davy, that's D-A-V-Y, came on board and, negated the postulation of Antoine Lavoisier and said, no, an acid must not contain oxygen as the most important element. However, he gave us an example and said, HCl is an acid. In fact, it is found in your tummy. Does HCl has oxygen? No. So on a strong note, as Davy said, that an acid is a substance that contains hydrogen, and hydrogen is the most important element in every acid. That was Davy's definition. As if that was not enough, Gay-Lussac came on board, and Gay-Lussac was about neutralization. Gay-Lussac said that acids are substances that neutralizes bases or alkalis when in contact with them. And one cannot separate an acid from a base. That if you must define an acid, you must include a base. That is Gay-Lussac's definition of an acid. An acid neutralizes a base when it comes in contact with it and loses its property from there. And then, if you check vividly, the definitions of Gay-Lussac's and Davy's actually make quite a whole lot of sense in chemistry today, because hydrogen seems to be the most important element. I use the word seems because there are other scholars that are coming. Hydrogen seems to be the most important element in every acid, right? And then an acid would definitely neutralize a base. So these two guys form the basics of the foundation of the fact that when studying acid and bases in solution, you cannot neglect their definitions. Now, years after, Svante Arrhenius, Svante, S-V-A-T-E, Svante Arrhenius in 1884 emphasized the importance of hydrogen in the definition of an acid. So he said, hydrogen is very important in an acid, that an acid, according to Arrhenius, contains hydrogen ion as the only replaceable ion when dissolved in water, and a base contains hydroxide ion as the only replaceable hydroxide ion when dissolved in water. That was the definition of Arrhenius. This definition was quite limited because it was subject to the fact that an acid is an aqueous solution that must contain water. What if it comes in other solutions than solids? So his definition does not hold ground. And that is where Bronsted and Lowry came into play. Bronsted and Lowry are actually two guys. Bronsted, also called Johannes Bronsted, then Lowry, also called Thomas Lowry, came into play and defined an acid as proton donors, while bases as proton acceptors. This definition, however, stood the test of time because it was not only limited to aqueous solution, but could be applicable even to solid solutions or solid acids and all that. However, this definition still is not the ultimate. Yeah, because acids can actually be defined without protons. Really? That's the truth. There are other acids that exist without hydrogen. Factual. For example, beryllium chloride is an acid. That's crazy, right? Aluminium chloride is an acid. Boron hydride is an acid. You know, very crazy stuff like that. Zinc chloride is an acid. It makes no sense, but it does. According to who? G.N. Lewis. Now, G.N. Lewis, also called Gilbert Newton Lewis, actually defined an acid as being an electron pair acceptor, while a base to be an electron pair donor. Details of what he is defining and saying will be discussed as we move down the plane. But for the scope of this study, we are going to narrow mind the study of acid, bases, and salts. Okay, let me say acid and bases on the definitions of Arrhenius, the definition of Bronsted and Lowry, and the definition of G.N. Lewis. Right? Good. General properties of an acid. Number one, they neutralizes the effect of each other. They react differently with indicators, litmus papers, methyl orange, stuff like that. And then lastly, they act as catalysts in many reactions. Now that takes us to the first guy, which is Svante Arrhenius' concept of an acid and a base. According to Arrhenius, in 1884, an acid is a substance that produces hydrogen ion as the only replaceable ion, which is an anion, when dissolved in water. Now, when you dissolve HCl in water, according to Arrhenius, we have hydrogen ion plus chloride ion. But the fact there is that this does not hold ground, because in water, hydrogen ion cannot be formed. You can't form hydrogen ion in water. Rather, you form hydrozonium ion. Why? Because the hydrogen from the acid will react with water to form hydrozonium. And then the chlorine becomes deficient of a hydrogen to become Cl-. So this is what he did not know. And of course, the formation of the hydrozonium ion is through coordinate covalent bonding. That's dative covalent bonding, to be precise. The hydrogen there does not contribute anything. You can draw the Lewis structure and you get what we say vividly. So the accurate write-up should have been, or if there was a way to redefine Arrhenius' definition, one would conclude that an acid is a substance that produces hydrozonium ion, as the only replaceable ion when dissolved in water. So, but according to him, he said hydrogen ion, which was totally awkward anyway. And then the same thing works with bases. So according to Arrhenius, or before we talk about bases, it's important for us to know monoprotic acids. Of course, they have one proton, like HCl, hydrogen bromide, hydrogen fluoride, and all that. Polyprotic acids are also called polybasic acids, okay? Like, for example, phosphoric acid and phosphate, as the case may be. And then, of course, the number of basicity of an acid determines the number of dissociation an acid can undergo, right? So you talk about H2SO4, we give you hydrogen ion plus HSO4 minus. Then HSO4 minus will dissociate to give you hydrogen ion and SO4 2 minus. As for phosphate, it will undergo 3 stages like that. Very, very important. Hence, the number of replaceable hydrogen ion determines the number of steps of dissociation an acid will undergo. Now, Arrhenius' definition of a base. He said a base contains hydroxide ion as the only replaceable cation when dissolved in water. And the fact there is as the only replaceable anion when dissolved in water. And the fact there is that he's actually in the quote correct, because when actually a base dissolves in water, it produces hydroxide ion. There is no hydroxinium ion, as the case may be. It's still OH minus and sodium I plus, if it is actually sodium hydroxide that is dissolving in water. If it is magnesium oxide hydroxide that is dissolving in water, it will give you 2 OH minus and magnesium ion. So that is his definition. So on the basic part, he has a kudos. But on the acid part, no, because of the formation of ammonia, of hydroxonium ion. That takes us to Bronsted and Lowry's definition. According to Bronsted and Lowry, these two guys actually define acid as proton donors, while bases as proton acceptors. And this definition gave birth to the concept of conjugate acid and conjugate bases. When an acid donates a proton, it turns to a conjugate base. And when a base accepts a proton, it turns to a conjugate acid. Very, very important. For example, I give you an example of HCl combining with water. HCl is the acid, water is now acting as a base. You will have hydrozonium ion and chlorine minus. Hydrozonium ion is the conjugate acid. Why is it conjugate acid? Because it received the proton and become H+. In fact, the best way to identify conjugate acids is the presence of excess proton when they are proficient with protons, and when it is positive, that's when you define excess proton. That's conjugate acid. As for conjugate bases, they are best identified with a negative sign when they lose a proton, when they become proton deficient, right? So that is that. So you can actually write a reaction whereby you have an acid giving you a proton and a conjugate base, and you give typical examples of that and all that, and that would just make the class a beautiful one. And the same thing works with a base. You have a base plus a proton to give you a conjugate acid, and you give multiple examples. You can take water on the acid realm. When water gives a proton, it becomes hydrozonium ion, plus OH minus. And then on the basic part, when water when water gives out, it becomes OH minus. When water gives out a proton, it becomes OH minus and hydrogen ion. The OH minus becomes the conjugate base because the water is acting as an acid. But when you go to the basic dimension, when it absorbs a proton, it becomes hydrozonium ion, which is a conjugate base, right? So very, very important, and one has to take note of this. So if you look at it very well, you discover that water has the ability to be an acid and a base at the same time. So for water to be able to perform as an acid and a base at the same time gives birth to a new dimension in chemistry called autoionization. How do we mean? The ability of water to self-ionize with itself to form a conjugate acid and a conjugate base is called autoionization, aka self-ionization. Water plus water will give you hydrozonium ion plus OH minus. Hydrozonium ion is a conjugate acid, while OH minus is a conjugate base, the same water. And that is the concept of autoionization reaction. It is also called amphiprotic reaction, or amphoteric substances can perform this. Now take note, the concept of autoionization is not only limited to water. There are other substances in chemistry that can autoionize or self-ionize within themselves. Typical examples of them are ammonia, ethanoic acid, hydrofluoric acid, and dinitrogen 2 oxide. Dinitrogen 2 oxide, or you can call it tetraoxonitrate, as the case may be. That's N2O4. They can undergo autoionization. And how is the reaction taking place? Ammonia plus ammonia, the first ammonia will lose a proton to the other one to become ammonium. Then the other one will be deficient with one hydrogen. That becomes N2 minus. As for hydrofluoric acid, it will form H2F, then the other one with plus, then the other one will be F minus. As for the dinitrogen, all you need to do, reduce the 2 to 4, and it becomes N2O, that is nitrogen 4 oxide plus nitrogen 4 oxide. Then one of them will lose to become NO plus, then the other becomes NO3 minus. You get it? Now, it is also important for you to know that even though these elements can undergo autoionization, the peculiar thing among them all is the presence of a hydrogen, which is always being donated, isn't it, and accepted. There are other elements that can undergo autoionization without actually making use of protons. For example, PCl5, that is pentafluoride, pentachlorofluoride, as the case may be, or phosphorus pentachloride, will perform that reaction to give you PCl4 plus and PCl6 minus. In other words, the PCl, the chlorine, is now going to be donated to one. The one that becomes deficient becomes PCl4 plus, while the one that becomes proficient becomes PCl minus. So here you are now donating chlorine. Is that clear? So that takes us to Lewis' definition of an acid. That is that for Bronsted and Lowry. Lewis' definition of an acid, according to G and Lewis, an acid is simply a substance that accepts an electron pair, while a base is a substance that donates an electron pair. A typical example is hydrogen ion and hydroxide ion. Hydrogen ion is the acid, hydroxide ion is the base. Why? Because hydroxide ion has 2 lone pairs of electrons, in fact 3 lone pairs of electrons, if you draw the Lewis structure. So the hydrogen will just come and partake and just come and click itself to it to form hydrozonium ion through coordinate covalent or coordinate covalent bonding, or simply put dative bonding, as the case may be. So if you check, hydrogen comes there to just sit without contributing anything, while the base provides the electron pairs, right? So as far as Lewis is concerned, electron pair donors are bases, while electron pair acceptors are acids. And another example is a reaction between ammonia and BCl3 and boron trichloride. Ammonia acts as a Lewis acid. Why? Sorry, as a Lewis base. Why? Because it has a lone pair of electron. As for BCl3, it has no lone pair of electron. It is an electron deficient compound. In fact, all electron deficient compounds are Lewis acid, while all electron rich compounds are Lewis bases. That's a very strong point which you have to put at the back of your memory, and you just have to remember that. Other examples of Lewis acids include hydrogen ion, iron 2 ion, aluminium 3 ion, zinc chloride, boron hydride, iron 3. You have here iron 3. I'm a little bit finding it difficult to see because it's a little bit dark. Maybe I can put on my torchlight and then things becomes better. All right, that's actually iron 3 bromide, and then bromine, and then you have aluminium chloride. These are acid Lewis. These are Lewis acid because they are electron deficient. Okay, aluminium ion is an electron deficient compound. Why? Because it only has 3 lone pairs. It only has 3 electrons in the outermost shell, which can be taken by a non-metal and makes it deficient of an octet configuration. It doesn't even have up to 8, not to talk of having a lone pair, So that's what makes it a Lewis acid. As for Lewis bases, you have chlorine ion, bromine ion, OH ion, iodine ion, water, ammonia, etc. Now, the reason why they are bases is because they have plenty electron pairs. Chlorine ion has 3 electron pairs, bromine ion has 3, OH has 3, iodine ion has 3, water molecule has 2, ammonia has 1 lone pair, stuffs like that. Now, Lewis acids and bases can also be identified in metals and non-metals reactions. In a non-metallic reaction, like where you have dinitrogen 1 oxide, laughing gas, reacting with sulfur 6 oxide to give you, no. Is actually means sodium oxide. Okay, sodium oxide reacting with sulfur 6 oxide to give you sodium tetraoxosulfate. Yeah, sodium oxide, not dinitrogen 1 oxide. It's sodium oxide. Sodium oxide here acts as a Lewis base because of the presence of a lone pair of electrons, while as for sulfur 6 acts as the Lewis acid because there is no lone pair of electrons. Remember, sulfur has 6 electrons in the outermost shell. The oxygen will occupy all the 6 electrons. There is no lone pair anywhere, so it is automatically the acid. And then also you can find this type of Lewis acids in reactions with metals. Metals reacting with water, for example, aluminium reacting with water to give you a very, very massive compound, that is Al in bracket water 6 raised to power 3 plus, and that is aluminium hexaaqua ion, or you can also call it hexaaqua aluminium complex ion, right? So the aluminium 3 plus is the Lewis acid, while the 6 water is the Lewis base. And this is where we stop as far as Lewis acid, Arrhenius acid and bases, Bronsted and Lewis definitions are concerned. And that takes us to the next part of this chapter, which is the strength of acids and bases. Boom.